Hello and welcome back to the main stage of the NASA TechRise virtual field trip. Thank you to all the students and educators and attendees here today. This is the main stage. So we have our keynote speakers here today, as well as throughout this session, there are booths where there are representatives from flight providers, there are representatives from future engineers, and there are past winner teams of the NASA TechRise Student Challenge there for you to talk to. And I am so excited to get this third session of our main stage going. This next portion is going to be called From Rocks to Rockets and Back, Insights from a Planetary Geologist. I would say in terms of job titles, Planetary Geologist is one of the coolest ones I can think of. So we're really excited. Here in a little bit, we're going to have Greg Peters from NASA's Flight Opportunities Program come and talk to you all about the excitement of planetary geology and sensing rocks and looking at terrain. And this is a really great fit for the rocket-powered lander option of the NASA TechRise Student Challenge this year, which is one of the flight vehicles. So I know some of you attending here today might know a little bit about the TechRise Student Challenge, and some of you might be new to it. So I'm going to kick off this main stage with showing a video that gives you an overview of what this NASA TechRise Student Challenge is all about, where you're going to submit a proposal idea of an experiment that could fit on one of these and be designed to be flown and tested on either a high altitude balloon or a rocket powered lander. So check out this video. You're also going to see some slides from some previous winning teams, and then we will be right back to kick things off with Greg Peters, all about From Rocks to Rockets and Back. So here we go with this slide presentation and this video.
This year's NASA TechRise Student Challenge has arrived, and this year's flight vehicles are the rocket-powered lander or the high-altitude balloon. 6th to 12th grade teams affiliated with a U.S. school can submit an experiment idea designed to fit in one of these and be tested on one of these. 60 winning teams will be selected to turn their experiment idea into a reality. The winners will have $1,500 and approximately 4 months to build their experiment. You'll get a cool box to build it in and technical support from our awesome team of future engineers advisors. And last but not least, the final experiments will be launched on a NASA-sponsored test flight. Are you ready to build with NASA? You'll learn a lot and get hands-on with an awesome project this school year. We encourage teams of all skill levels to submit your experiment ideas and join this year's NASA TechRise Student Challenge. Go to futureengineers.org/NASA TechRise to learn more.
All right, so you got a glimpse of some of our previous winning teams getting hands-on building their payloads. But as a reminder, it's a multi-step process. The first step is to have that great idea and make a 3-page proposal and submit that by October 20th. And those ideas will get judged, and those that are selected as winners will get $1,500, a really cool winners build kit, and advisory meetings with our awesome team of mentors. But that first step is getting that idea. And we know that can kind of be the hardest part sometimes, is what am I going to do for an experiment? What kind of experiments could I do on a rocket powered lander? And so I'm really, really excited for our next session. As mentioned, we have Greg Peters from NASA's Flight Opportunities Program, and he's going to be talking to you about from rocks to rockets and back, insights from a planetary geologist. Greg, I'm going to go ahead and introduce you, but feel free to come on whenever you want. So Greg, during his career at Jet Propulsion Laboratory, hey Greg, held many roles across multiple projects and missions. Most notably, Greg served as a surface scientist for the Mars Science Laboratory mission, the project scientist for Lunar Puffer Instruments development, and the cognizant engineer for Mars Analogs development for the Mars 2020 Perseverance mission. In 2007, Greg received a NASA Space Act Award for conceiving RASP sampling technology, which was flown on the Phoenix Mars mission. RASP sampling provided the historical first water ice sample ever taken on another planet. That's like huge, guys. In 2017, Greg received a NASA Voyager Individual Award for his work in determining rock properties from the MSL drill telemetry. Currently, Greg is an AST technical manager under NASA Armstrong Space Projects and Partnerships branch for the Flight Opportunity Program, where he works with technology developers and industry flight providers to increase technology spaceflight readiness through suborbital test flights. And as a reminder, all of these NASA TechRise experiment ideas you have are designed for suborbital test flights, which means they go up, they get tested, and they come back down. So Greg, I'm so excited for you to be here. Thank you so much for coming and speaking to our students here today on this virtual field trip. I'm going to give you the stage. I know I have some slides to share with you. So do you want to start things off first and then go to your slides, or do you want to bring up?
We can do it however you want. The slides are just pretty pictures, and I can we can speak to the slides, or we can just have a conversation. But if you'd like to toss them up, we could probably just go to the first one.
Yeah.
They're
pretty awesome slides. So let's start with the slides, and you'll give an overview to the students all about your amazing background, and then we'll keep it conversational. And as well, there's a Q&A up there. So if anyone has any questions throughout this session, you can submit those and we'll take them live here on stage. So hold on, Greg, while I get these slides up here. All right, hopefully you see this. All right, take it away, Greg.
All right. Yeah, that's a cool picture. That is a artist rendition of just how that's like Wild West version of the Mars Science Laboratory shooting rocks with lasers and getting ready to drill them. So, so that is one of the missions that I did get an opportunity to work on. It was super cool stuff. But Dan, let's just push to the next one, because so hey, thank you everybody for your interest in all this stuff. Deanne and our friends over at Future Engineers asked me to come and talk to you about and maybe describe my path to becoming a planetary geologist. It'll probably be a little unexpected, actually. So in short, any success that I had in my career, it was not because I started out as particularly smart, actually. It's really been an example of just how having like a good attitude, a willingness to follow like opportunities, and if you have those things, it'll take you on some pretty cool and unexpected adventures. Now, people will tell you all the time to follow your passion. And I recently heard Mike Rowe, he's that guy from the TV show Dirty Jobs. And he'll advise people that you should follow opportunity, but bring your passion with you. And I agree with Mike, because as I reflect on it in my own career path, that I pretty much followed that model. So, as a young person, did I set out to be a planetary geologist? Oh, I did not. I grew up out in the middle of nowhere in the high desert of California. The closest town, I think, to the little homestead that I grew up on had a population of about 2,500 people. My dad worked for a borax mining company. And we even lived on a small mining claim for a while. Now, living in the middle of nowhere, that can be a drag, for sure, but it offers some advantages. So from a pretty young age, I learned how to drive. There was no traffic, so I learned how to drive. I learned how to operate a backhoe. My dad was and still is quite the craftsman. He's a mechanic and a welder, a carpenter, and just an overall builder of things from the ground up. And so early on, he taught me how to think about how complex things, are designed and assembled. So any ability that I have to think about geology as a set of complex systems, well, that started probably when I was your age, when I was working or playing rather in my dad's shop. So beyond working in his shop, my father taught me how to look for and pan for gold. Now, as a fun aside, field geologists, they become astute observers of the environments in which they occupy. So if you ever want to become a good observer, try watching a stream as it curves and twists and tumbles over the rocks. Try to imagine where bits of heavy metal like gold might accumulate. And that'll help you become an observer. Those types of activities will help you become an astute observer. Geologists are always looking down, right? Because they're always looking for something different. They're always looking for what's different in the landscape, right? Now, if you'd have asked me then if I was passionate about geology, I would have said not particularly. And I'll add, I was not a good student in high school. In fact, when I was 16 years old, I made a huge case to my parents that I was going to quit school. I was going to get a job. School was a waste of time. But by sheer determination of my mother's insistence, I did manage to graduate high school by the skin of my teeth, I'll add. I worked for a while at a gas station. I held jobs driving trucks. I eventually found a job with this mining company. And I was hired there to drive trucks, operate mining equipment. I'll admit that like running bulldozers and these giant front end loaders and operating rock crushers and screening plants, those are all worthwhile skills to learn, and it can be kind of fun, actually. And I've always had a ton of respect for the people who do these kinds of highly skilled jobs. But even then, I wouldn't have described myself as being particularly passionate about that work. I was passionate about something. My big plan was to become I was going to be a famous bull rider. That was it, right? I had it all set. So rodeo was my passion. And I spent a good deal of time on weekends strapping myself to these angry 2,000-pound animals, trying to stay on them. And I was following my passion after all, right? I understood all the various techniques. I had studied it. I knew what was going on. I had the courage, right? But what I didn't have was an abundance of skill and athletic ability. So during the week, it was back to the mine, as they say. So I'll say that, bouncing around in a front end loader with bruised ribs, if that's an experience I do not recommend to anybody, by the way. So how did I end up on this road to becoming a planetary geologist? At the mining company that I worked for, there was an opportunity to help set up and build this quality control department. They needed calibrated geotechnical testing that would allow them to bid on these state supply contracts. Boring, right? But hey, this was a chance to learn something about the testing, about the mechanical properties of rocks, and it sounded kind of interesting. So I inserted myself with a geologist and this geotech engineer that the company had contracted out to help us set up this capability. And I spoke up. I said to my boss, "Hey, I'd like to learn how to do that." And to my surprise, the company just put me in charge of the project. They're like, "Hey, these guys that we've hired are going to go away. Somebody's got to run this thing. So learn as much as you can." And and here's a bit of a life lesson that in the context of your future careers, always ask for what you want. Don't assume people know what you want. If you ask and you're sincere in your willingness to learn something new, and you're willing to put in the work, you'll find that people will bend over backwards to help you get there. And they did for me. In this new role, I helped build this laboratory, and it's a pretty fancy word because we called it a test shack. It was actually built inside this old construction office trailer with wheels so that we could move it, from one field site to the next. I helped source and set up the equipment. I spent a lot of time in the field learning how to properly pull and get representative rock samples. I helped run the tests, and I eventually learned how to prepare the reports. And it was that experience with these grouchy old guys who, for some reason, decided to take me under their wing that actually fueled my interest in geology. And I remember, thinking, God, wait a minute, am I developing an interest? Am I developing a passion for rocks of all things? What sorcery is this? And I found that I was asking lots of questions and, well, what makes some rocks weak and others strong, and what are the processes that what are the processes that determine where we should look for the rocks that will represent the best products for us? And it turns out that geology holds all of those answers. So I read everything that I could, about geology. I tried to create for myself a foundational understanding of geology and geotechnical engineering. And, this is before stepping onto a college campus. And I'd like to, point out that this is very similar to what you are all doing right now. You're thinking about and you're learning about, you're taking part in deciding what types of sensors or what experiments that you might want to fly for this competition. Well, that's one way of setting you up to take advantage of opportunities that will invariably present themselves to you in the future. So, and I'll just say, even if your team doesn't get selected to build and fly a payload, this process of learning and thinking about the measurements that you want to take and the experiments that you want to run, the questions that you want to find answers to, this is going to set you up for success. Your brain is going to get pre-wired to think about different ways to solve complex problems. And that's what engineers and scientists do every day. So when opportunity presents a path, and it will, you'll be better equipped to follow it just by going through these thought processes.
I'm taking on the slides because it's like the most motivational thing.
Okay.
And I'm like, we need you, big screen.
Okay. Thank you.
Oh my gosh, your story is phenomenal, and it's
thank you.
Yeah, it's just great to hear. I mean, everyone's path is different, right? Some people are young and they're like, I'm going to be an astronaut one day, and they become an astronaut, but I'd say that's probably a small percentage. We all kind of meander in all these different ways, much like you were saying, if you want to be an acute observer, look at this water, going about and where it's depositing things. But I feel like a lot of our lives are like that, kind of meandering about. But it's amazing to kind of see how, I mean, you were really like digging in the dirt
digging in the dirt.
And riding bulls and everything, and somehow parlayed that into planetary geology, which is amazing.
Parlayed is a good word. Yeah, they did get parlayed into it, right? So like I said, it didn't start out as a passion, right? It was experience that I had gained. It was opportunity that I was willing to follow, right? And really the experience that I learned about geotechnical testing first, and then geology, that actually brought to me this incredible opportunity, or at least it brought me to a place where I could, follow an opportunity. There was a planetary scientist by the name of Jackie Green from Jet Propulsion Laboratory. She called our company, and she was looking for some special materials that she hoped that we could mimic the physical properties of comets. And comets, these icy, planetary bodies, right? But it's really expensive to try to to try to test in really cold environments. So she hoped that, perhaps we could do that in a more ambient temperatured environment. And I worked with her, and I helped her build these test articles. I helped her I helped her run this test to do this anchoring system for a mission called Comet Nucleus Sample Return. Now, it's kind of disappointing because Comet Nucleus Sample Return never actually flew. But this is one of these bright bright linings, right? For me, something way better happened, right? I got an opportunity because of that. As it turned out, Dr. Green was setting up this new laboratory at JPL to develop planetary simulants as a new capability for JPL. And she asked me if I'd come over, help her set up her lab. And of course, it took me like a half a second to say, yes, I'd love to do that, and she called it, and it remains the Extraterrestrial Materials Simulation Laboratory, or the EMSL is the acronym. That's how the acronym is, for the EMSL. So when I say EMSL, if I say EMSL later, you know what I'm talking about.
And for everyone here, JPL is Jet Propulsion Laboratory, which is in California, and there's a lot of specialization in Mars. That's where the Mars rovers are built, and it sounds like a lot of the instrumentation that you've worked on is from JPL as well. And I also want to backtrack and just explain, obviously, geology. I think students have an idea of that. They take earth science courses and learn about geology. Can you kind of bridge the gap to planetary geology? Like, really, what is that field of research, and what is that all about?
Well, there's a lot of similarities, actually. So certainly in planetary geology, there's the bridge over to the rocky planets, Venus, Earth, Mars. Certainly on the geology side, and so you can observe a lot of things that are happening on Mars, on Earth, and relate those processes to Mars, even though the environments aren't always the same. The old question is, well, what are the rocks like on Mars? And we say, well, what are the rocks like on Earth, right? Because there's just no one thing. And I can remember when the MSL mission, that's the Curiosity rover, landed on Mars. The very first picture that came back, and I remember even though we knew, you still kind of had this in your brain that, well, Mars is this volcanic planet, right? It's the basalt planet. It's the red planet, all these basalts and stuff, right? And it landed at Gell Crater, and the camera system, before the rover had even driven off of the platform, there's this beautiful panoramic picture of all of these beautiful sedimentary, layers and layers of sedimentary rocks. Just kind of clicked over. Wow. Mars has this incredibly diverse geology that's much different than you would think. And even though we knew it was there, seeing this grand picture in front of you and knowing that we were going to go get to explore that was pretty exciting. Deanne, you're muted.
And in terms of understanding other rocks, whether it's Mars or on the moon, what is that really? Why does NASA want to know about rocks? Why do we want to study rocks?
Well, because geology tells the story. Geology is what tells the story of the history of all of these planetary bodies, Earth, the moon, Mars included. And I would just say that it's not easy, right? I mean, even on Earth, developing the right tools to accomplish what you want to accomplish is a difficult task. You have to send robots, right? You got to send robots and arms stuck to these rovers, and those become pseudo field geologists for you, and and I can talk a bit about that, right? In how that ties to this particular competition. Hey, this is tough. You have to you don't actually go out there and touch the rocks in person, and you got to figure out what's there. So you got to build instruments to do that. So scientists need engineers. Engineers are the ones who have to invent, design, test, break, rebuild these systems or these instruments that we send to to these other planets to learn as much about them as we possibly can.
Yeah. So if we talk about TechRise specifically, there's two vehicles this year. There's the high altitude balloon, and then there's the rocket powered lander. And for those watching, if you're not familiar with rocket powered lander, I just got a prop. So if this is the rocket, essentially in Mojave, California, this thing is going to go up, and it's going to go across. It's going to basically like kind of traverse around a lunar surface test field. So I know we're talking a lot about Mars, but for TechRise, there's a lunar surface test field. So it's down here in California, and it's designed to look like the moon. But the challenge really is to think about what kind of experiment ideas you might want to put on this rocket-powered lander, to understand that terrain down below you, those rocks down below you, some of the terrain might be smooth, it might be rough, like all these different things. So obviously these test flights are designed because they're used by professional engineers all the time at NASA. So can you give me an example of kind of how this type of technology is used with terrain by professional engineers? For example, like terrain navigation or something like that. Yeah.
Sure.
Yeah.
Sure. So there are, well, in most cases, or in some very important cases, you may want to use, systems that use lasers that precisely measure how smooth or rugged a surface is, so that you can safely land there. You may have indications from other instruments that say, hey, there's something interesting down there. There might be water ice or something in this permanently shadowed region or whatever. And so you're like, well, I'd like to put a spacecraft right there. Well, it turns out these permanently shadowed places that may harbor these volatiles. We call them volatiles, which is a fancy word for saying, water ice in a lot of cases, or other materials that if they get heated up, even just get light shined on them, will quickly sublimate away. So the conditions that create the ice that lives in these permanently shadowed regions are sloping terrains and low angle lighting, which those are conditions that are hard to land in. And so a LiDAR system might be something that you would use. And there may be other instruments that you want to use to observe or make measurements. There may be optical systems, that can see in spectrums beyond what our human eyes can see. There may be spectrometers and what a spectrometer does is it parses out the spectrum, the electromagnetic spectrum, and it'll measure the intensity of each of those wavelengths. And those are those are signatures for what's there. So that if you can calibrate for that, you can be like, oh, I see this funny line, and I know because of the shape of that funny line, I know what's there. It may be an accelerometer, right? They can just feel the slightest movement, like less movement than we can even feel, right? Or it may be a sensor, that sniffs at the air and it can report back here. What is the atmospheric chemistry here? So there's just a small example of the types of sensors and instruments that an engineer might design and a scientist might be able to use to learn more about whatever it is that they're interested in learning.
And even just basic cameras, right? Like just
even cameras, the world of information. You're absolutely right. Field geologists spend more time on Google Earth than they do out in the field nowadays, I think. It's because get really good images.
Really good images, stitching them together, using them in different ways. So, obviously NASA has missions to the moon and NASA has missions to Mars, but there's a lot of value in testing before you go, right? Because there's when you go to Mars, you get your one shot and your one shot only. I know we've talked about this lunar surface test field. I think at JPL, there's a Mars yard, right? So I guess just talk to the value of kind of, testing things here on Earth before you go and do it in an actual mission.
It's important. It's really important. And it's not only important to just test the things, but when you're going to go into another planetary environment, it's important to test in the relevant simulants, right? And that's just like a sales pitch for me from the EMSL days. It's like, hey, you guys are gonna have to bring us onto your team because you guys really want you guys really want the right rocks to test in, or you want the right regolith simulant to test in, so that you know that your system is going to work when it gets to Mars or when it gets to the moon. On top of that, you might care about the environment in which that entire system is placed. If you're trying to scrape up water ice, for instance, you certainly want to know how it's going to behave in this low pressure, this low atmospheric or no pressure environment. So we're like I mentioned, things will sublimate away. You get down to this precious ice, that's hiding there on the moon, and you expose it, and then it all sublimates away. Then you're going to be pretty bummed out.
So the moon specifically, I know you talked about water ice, and I guess in general, obviously the Artemis missions, and we're focused on the lunar South Pole and looking at water ice and trying to find water, which is a valuable resource. But as someone who's passionate about rocks on other surfaces, I guess talk to me about lunar rocks. Like why, how is that different than a rock here on Earth? Like talk to me a little bit about the characteristics of lunar rocks and what makes them a little different.
I would say lunar rocks are slightly less diverse. Now, these are also definitely, these are up for debate. Like, science is always a conversation. And so my opinion about lunar rocks may be different than somebody else's. And I've given it away that I study more about Mars than I do about the moon, right? But
well, we can start with Mars. What's different about the Mars rocks?
Well, not as much as you would think, actually. So the Mars rocks are. I'll just talk about Mars in general, right? So Mars and Earth. This is super interesting, by the way. Mars and Earth were kind of on this like same track for a really long time. Both were warm. Both had liquid water on their surfaces. Both had thick atmospheres. And then I'm going to mess up on the timing. Couple billion, 3 billion years, something like that, years ago.
Billions.
Mars lost its atmosphere, right? And so it kind of put it in a bit this like freeze-dried environment. So we have this environment on Mars that stopped having the same kind of water cycle processes that we have on Earth, right? We're used to this incredibly dynamic water cycle. We get regular rain. Our mountains are constantly being built and torn down, and on Mars, that's kind of on hold. It got put on hold. But about the time that life was starting to form on Earth, Mars was still wet and still had this thick atmosphere. So it's reasonable to think that it's possible that if life was starting here, microbial life was starting here, it could have been starting on Mars. And so that's why the Mars Perseverance mission, that Mars 2020 mission, is going to the places that it's going, because it's kind of looking for those signs. If you're going to look for life, you're going to look for it where the water was. And so this floodplain at Jezero, even Gale Crater is a good candidate, for places where where life could have formed. There's enough energy, enough solar energy there. It was wet enough, and so it's pretty exciting. And the day that we find it, if we ever find it, it'll change everything we know about life, because we can know that there's billions of other galaxies, each with billions of stars, and we can easily say, oh well, it's pretty easy to think, oh, there's definitely someplace out there that's harboring life. But until we actually find it, we can't say for sure. And until we find it, this is it. This is the only spot that we've ever actually found life is on Earth.
Right. And I know you mentioned earlier that like rocks are basically storytellers, right? They tell a big story. So analyzing those rocks on Mars is a big deal because we understand that story better. I want to make a big distinction for everyone watching. When you're doing your NASA TechRise experiment, there is no rock collection. So even though Mars is doing that, like looking at samples, sample return, and things like that going forward, TechRise is really like planetary geology 101 in terms of like, how do we take pictures of things? How do we understand these different terrains, and I don't know, there's a million things that you could come up with, but I just want to make sure, you're not scooping up rocks with these, but think about cameras, think about lasers, think about sensors, think about accelerometers, so you know the position of it and things like that. And one of the things you can think about is understanding those rocks, the rocky surface that's down below there. So I know you talked about Mars, but then obviously the lunar surface test field it doesn't have actual lunar rocks. It's, like just designed to look like a lunar surface test field. But there's a lot of things to explore and a lot of ways to kind of dive into that technology. And NASA's doing this all the time, right? NASA's going to the South Pole, and they have to think about how they're going to land there, where they're going to find a good landing spot, what is the characteristics of that landing spot, and all of those different things. So it's a really, really cool opportunity. I have some questions here from the audience. I think the question I have here is interesting. For gaseous planets without rocks, how can the history of the planet be determined?
Ooh.
If you don't have a rock as a storyteller, what kind of things can you do? And if you want to punt on that question,
Yeah, because otherwise I'll say something dumb like if it doesn't have rocks, it's not worth going there.
you're like, I'm a planetary geologist, not a planetary gasologist. I don't know what that term is, but I know someone at NASA knows the answer to that question, and we will follow up and we'll make sure we get that for you. What excites you most about the future of NASA missions and space exploration? And I guess in particular, what excites you most about the future of planetary geology and the work that NASA's doing?
Well, I'm very excited about the prospect of someday bringing samples back, which may be a long time, right? Bringing samples back from Mars. I'm very excited also about just in NASA, or I'm sorry, in general, NASA's ability to just continue to expand its ability to explore. We can send robotic scientists to other places, and it's very exciting. Don't get me wrong, it's very exciting. But the best thing to have on that surface is a geologist out there, boots on the ground, tools in hand, out there doing field geology. And I say doing geology. I know people will be, oh, you don't do. Well, you do. If you can do science, you can do geology. I would argue. And so I'm really excited for we've had one scientist, one bona fide scientist go to the moon. We're going to be sending others, and then someday hopefully I'll get to see that we send scientists to Mars.
Amazing. It's amazing to think about that. And I love it. I think everyone's vying for their own field. Like, no, we need engineers on the surface. No, we need planetary geologists. And I think the reality is, like, I think our future astronauts are going to wear a lot of hats. They're going to be farmers. They're going to be geologists. They're going to be engineers. They're going to be doctors. They're going to be very multi-disciplined to be able to go and go to these places. But bots before boots is what I've always been told. We got to send the bots first. We have to send the landers. We have to send, sensing technologies to understand those things. And then we get the boots on the ground with astronauts. So really cool stuff. I'm going to take a moment. I know you have this slide deck. I'm going to fast forward to the last slide, just so that students get an idea of what this rocket-powered lander looks like and what the lunar surface test field looks like
Good
here.
idea.
So give me 1 second. All right. So we talked here. It's a good example of lasers. I think lasers are definitely a possible sensor. And I should remind everyone that if you go to futureengineers.org/NASA TechRise, there are slide decks with ways to brainstorm different experiment ideas that you might want to come up with that could go on a rocket-powered lander or a balloon. There's 2 vehicles, but I know we're focused a lot on the lander on this talk. And then there's also different component lists of different possible sensors or different cameras or different things you might want to think about. So as mentioned, I think this is from the moon, obviously, and there's a lot of scientific potential. But if we look at this here, we've got the Astrobotic Zodiac lander. That is one of the flight providers this year that's going to be flying NASA TechRise experiments. And so 30 winning experiments flown on this vehicle, and they're going to be mounted up at the top of that ring, and they're going to go up for a test flight. And that rocket-powered lander is kind of going to traverse around this 100-meter by 100-meter test field. And so it's really important to think about what you can design. So as I mentioned, you're not going to be collecting rock samples, but what can you learn about that surface? What can you learn about those rocks in that process? So I don't know if, Greg, you want to talk about, I know you mentioned some sensors before and different things, but I guess tell me a little bit about the excitement of this opportunity.
Well, I would just say that every
engineers.
I would say that every mission to the moon or another planet is usually predicated by a mission that flies over an area, either orbitally or closer. So thinking about what you can learn as you fly over a surface is going to be important. And I think that Future Engineers has done a fantastic job of kind of seeding some ideas for that. But I got to say, I cannot wait to hear what y'all come up with.
And I don't even know if you know this, Greg, but we're also going to be planting some little secret gems of objects on there. So in terms of, identification, I know we talked a lot about rocks, but we're going to have different things there too, a little bit of a scavenger hunt for teams. So that could be a possible experiment too that you put forth, is putting sensors on board that might be able to distinguish one thing from another, whether it's using a camera or whether it's using a different kind of sensor as well. So all kinds of great. I'm going to zoom back out, but we've all seen this. So we've got a few more minutes here. If you guys have questions, we're going to take this. We have a question about Osiris. Is that something that you know a bunch about? Or
I don't know much about Osiris-Rex.
Okay. And then we have one. I think there was someone asking if you were involved with Osiris-Rex. So I don't think you're involved with Osiris-Rex, but they did just return a sample from an asteroid. So I don't know if you want to speak top level about what's different about an asteroid and why that's cool and what kind of story those tell, just in general.
Yeah, so asteroids are important for two reasons. We'll just talk about the bad reason first, right? Asteroid. We'd like to know more about asteroids because you got all these asteroids zinging around, right? And so we want to track them, so that we can say, oh, hey, in 150 years that one might come close or whatever. The other and you want to know about the properties, the physical and mechanical properties of those asteroids, so that you can try to figure out, devise ways to do something about that. The other thing is pretty exciting. It's asteroids represent an opportunity to get resources from someplace other than Earth, right? Everything that we've built, or everything that we use today is from some resource that was either dug up or grown, dug up out of the ground or grown right here on Earth. And so once we start getting out, learning how to access asteroids, there's this whole asteroid belt between us and Mars. Once we figure that out, then there's more abundance of our raw materials to work with.
Great stuff. There's so much to be discovered. And I know what you work on is, one sliver is obviously specialization in Mars, which there's so much going on there, but we've got asteroids and we've got lunar exploration and obviously beyond even that. I guess tell us something that excites you the most about working at NASA, and then also we'll start pivoting towards an exit, just about kind of sharing some encouraging words for the students. So what excites you most about working at NASA?
So, well, I will just say that NASA, well, just exploration in general, and NASA. But I would say that a really exciting thing is this golden age of commercial space that we're actually entering into. And I like to kind of harken back to this golden age of aviation, that if you're into that history and you read about that, there was thousands of different experiments going on. People who were, bicycle mechanics and tinkerers and electricians and people working in their garages, by the thousands doing all these experiments, failing most times, succeeding in other times. And that environment created the first flight. We had this first flight of a powered aircraft, and then within 30 years, we had dependable air travel, right? And that was a result of people willing to take a risk, people willing to follow opportunities and follow these these different paths. And I think we're in that with this with space flight right now, with commercial space, right? And NASA plays this incredibly important role. NASA needs to keep doing things, these cutting edge things that quite frankly, you don't make money at because they're not a profitable thing, but the things that need to be done. But we're on this cusp of, I think, this commercial market that's going to just blow everything up. If we're going to become, a spacefaring civilization, we need that, and I think I see it. We see it on the horizon. It's incredibly exciting.
And all of those commercial companies have to do develop these new things, test them here. And I know Flight Opportunities works a lot with this kind of fast ground-based or suborbital test flight, prototyping. It's really, really awesome that as students, you get the opportunity as young as 6th grade to do basically the same thing that, aerospace engineers and scientists and planetary geologists are doing every day. So I know we have a question here, but I think we need to wrap up about a little bit more about laser and LiDAR technology and planetary exploration, which is remote sensing. But I'm going to say that I'm going to refer you to the website with some of the resources that we have there, because we're going to wrap up with Greg here. So Greg, the students, the big ask here is put in a proposal. You don't have to build anything yet. You need to put in a proposal by October 20th of an idea of an experiment that could fly on either a high altitude balloon or the rocket powered lander, which we just showed that slide of. So it's a big deal to come up with an idea that you think NASA is going to think is interesting. And I should just say, it's not just NASA thinking it's interesting. It could be something really basic that just is developing your own technology skill set. It could be something that's changing the face of space exploration. You take it at the level that you are at. But what's most important is you just, try to find that spark, try to find that thing that motivates you, and figure out how to put that proposal in. So Greg, just some parting words here, and then we're going to send students off to the booths and we're going to say goodbye. So what encouragement do you have for students putting in a proposal?
Remember that it's hard. Embrace the difficulty, right? Whenever we've mastered a game, we stop playing that game, right? Because it's no longer a challenge. So just remember that, and always have fun. Just have fun with it. There's the coming up with the idea part, and then there's the trying to figure out how to solve, what measurements do I want to take and how do I take those measurements? What do I want to observe and how do I observe it? Just remember that that's all fun. It's all fun stuff. So, and just as a parting last bit of unsolicited life advice, I would just say that, one, there's no set formula for success, so if you're trying to take notes, there is no formula, right? You have to give yourself permission to try something new, and remember that the most unexpected opportunities, they can bring you places that you never dreamed possible. So that's it. I'm really so looking forward to learning about the ideas that you come up with for this challenge.
I can't wait for you to see some of those proposals. Well, wonderful, wonderful. Thank you so much, Greg, for being here and sharing all the wonderful work that you've done. It's really inspiring. And students, we have some more booth time. So over at those booths, we have past winning teams and educators that are there. We have representatives from future engineers that can talk to you about that proposal. You need a what, a how, and a why, 3 pages maximum. So if you have any questions about that, you can go there. And also we have representatives from Astrobotic. Remember that cool rocket-powered lander? They can tell you all about that lander. They're over in those booths. We also have representatives from Worldview who can tell you all about the high-altitude balloon test flights. And there's much to explore. Just want to say thank you to all of our students and educators and everyone that is here as well. If you have any other questions, you can always email support@futureengineers.org. We are here to help, and we are so excited to answer any questions you have as you go forth and make those proposals before that October 20th deadline. We can't wait to see your exciting ideas. And thank you again for joining here today. And beyond this, the website has a ton of resources. So futureengineers.org/NASA TechRise, lots of slide decks, lots of videos, lots of cool stuff. So we encourage you to check all of that out and let us know if you have any questions. All right, so we're going to sign off now and send you to the booths for just that final bit of interaction and mingling. And thank you, and have a great rest of your day.